Hi, we're Giovanni, Alex and Ricardo, three of the PhD students in the particle astrophysics group of Professor Laura Baudes. We're involved in various activities in the context of the Xenon Dark Matter project. Here on campus, we're 8 researchers, between PhDs, postdocs and faculty members, but we're part of the much larger Xenon collaboration that currently connects more than 170 scientists from 27 institutions all around the globe.
As physicists, we try to understand the universe at its most fundamental level. Recent decades saw great progress towards this goal. Nevertheless, we still do not understand what the majority of the universe is made of. Have you heard about dark matter? We did. Within the Xenon collaboration, we aim for direct detection of one of the most promising dark matter particle candidates, the weakly interactive massive particle, or WIMP for short. We are using a ton-scale liquid xenon dual-phase time projection chamber placed deep underground at Laboratorio Nazionale Gran Sasso, under the Italian Apennines.
Well, but building and running the most sensitive dark matter detector takes a lot of planning, a lot of effort and commitment. But its principle in the end is rather simple. We want to detect particles. To get to the Xenon target though, a particle needs to cross all the Gran Sasso mountain, the passive shielding surrounding the cryostat itself, and finally, it bumps with the xenon atoms. In this process, both light and free charges are created, which we see with our sensors. Later, these are used to reconstruct the properties of the particle. Most of the interactions we record are actually known backgrounds. However, we expect that at some point, we'll notice some interaction that does not fit into any known background. If this event has the signature of a WIMP, well, maybe it could be the missing piece on the hunt for dark matter.
This exciting type of experiment opens a wide variety of different tasks where one can contribute to cutting-edge research.
Up to date, the brand new detector Xenon and Ton is starting operating. As part of the Xenon group, I've been deeply involved on its photosensor, the so-called PMTs, which even if they are capricious, they allow us to detect any events inside the TPC. We have 494 PMTs, 120 of which were tested here at our labs.
Besides data analysis, our group is also involved in hardware and work on site at the Laboratorio Nazionale del Gran Sasso. At the beginning of the year, we participated in the installation of the new TPC for the Xenon and Ton experiment. In particular, our group was deeply involved in the assembly of the 494 PMTs for their light calibration system and for their cabling, consisting of more than 16 kilometers of cables, and you can see some of them in the background.
I've been doing the full 3D simulations of the electrostatic fields in the detector. These simulations give us how the electric fields behave and therefore how the charges move around in the 3D space, and where they might bump into the walls of the xenon volume, leading to a lost signal. This is of very vital importance. It's a fun task to model the geometry of the system and study these important features, but some simulations can be quite stubborn and hide their bugs very well. It's an interesting challenge to get them to work.
If on the other hand, analysis of unique measurement data is more your thing, you might be interested in hearing that our group is also highly involved in that. Not only does Xenon hold the current leading exclusion limit on the WIMP nucleon scattering cross-section, but is also probing a wide spectrum of other physics channels beyond dark matter, such as neutrinos or decays. I'm recently involved in a refined search for the 2-neutrino double electron capture in Xenon, a rare process with the longest half-life ever measured directly that was first observed by Xenon 1 last year. You might have also heard of the just recently seen excess electronic recall events, which cannot be conclusively explained yet, and I'm looking forward to contributing to the efforts of unraveling this puzzle with data taken by Xenon and Ton in the near future.
To perform all these physics studies, we have to find a very large signal over a certain background, and if we want to succeed, we need to know this background very well. At this point, the simulation background plays a very important role, because with our tools we can simulate this background event over a very long energy range. With our tool, we can simulate background event coming from the material used to build the detector, and also background event coming from the interaction of cosmic particles.
In the end, this is just a glimpse of what we do here. If you're interested, contact us to know more.
Enjoy and stay safe.